further behind than we are, but just in the interest of just showing what this Shiny package is, let me show. Okay, so there's the data tab, there's a canonical correlation tab, there's a tab for global adjustments, and there's a tab for differential expression. I'll show the differential expression tab real quick. So I'm going to be looking at the original data. You can also look at the centered data, and although I won't show this right now, you can also, if I define an RUV3 adjustment in the global adjustments part, there will be an option here to start off with that RUV3. So I'm going to define a factor of interest, gender. I'm going to define as my negative controls the housekeeping. And then here you see I've got the p-value histograms, the empirical CDFs. I can define as positive controls. These are the genes from the XY chromosome. I'm going to look just up through the top 50 genes, and I'm going to define the y-axis here. Y-axis will go up to 25. Okay, so then I can get a plot like that. And I can, for example, see the unadjusted analysis. This is what we saw in the slides previously. You have this horrible looking p-value histogram and a not so good looking rank plot. And if you do the RUVR inverse, it looks quite a bit better. Coming down here, there's the projection plot, there's a volcano plot, there's this variance plot, and then also here I've got all the various genes, and I can do something like click on this one, and if I was connected to the internet, Google would pop up with a Google search of RPS4Y1, and I can just immediately look at it. It works now. Yes, so see, I can immediately investigate those genes. I can also, for example, draw a box around these, and I see that those two are KDM and UPS9Y, and I can click on that, and it'll Google search it for me. So it's nice and interactive. The one thing that I wanted to point out conceptually that's going to be relevant to the projects that you're working on in this session also. So remember I said that interpreting this canonical correlation plot is a little bit tricky. There I showed an example with region, but with gender and the spike in controls, you get this nice low correlation, so you're pretty convinced that they're safe. Let me close this. And where is this? Okay, so this, all of that, what I just showed you was with a balanced design. In the next example, I do an imbalanced design, and basically what I do is I take the same data set, but I drop all of the males from Davis, and I drop all of the females from Michigan. So now I have this very confounded design. Okay, this is somewhat artificial, obviously, but I just want to illustrate that the methods still work in this case, and also that you need to be a little bit careful in your interpretation. Okay, so let me pull up the Shiny app here. So again, this is with the imbalanced design. I've artificially induced a lot of confounding. If I go to this canonical correlation plot, which is the first thing that you'll always want to do, I'm going to look at gender, and I'm going to look at the spike in controls. And now I see that actually the first couple principal components of the spike in controls are actually very strongly correlated with gender. And the reason is because of the confounding of the study, not because the spike in controls are bad negative controls. Okay, so that's the important point to be made there. If I go to the differential expression, and I'm going to do it with gender, I'll just keep the housekeeping genes, and we still end up with a very nice p-value histogram, despite the fact that we had this strong confounding. just for sake of comparison, the unadjusted analysis actually looks pretty bad. So now the histogram looks bad in a different way. It's actually very left shifted. But as a way of knowing that this is not actually real biology, that this left shift is artificial, if you look over here at the empirical CDFs, you see that the negative controls and everything else is very strongly left shifted. If you're not willing to believe that all of the housekeeping genes are differentially expressed, then this is a tip-off that things are bad. You can also look at the positive controls again. Again, this is always very, very useful. So I'm going to put the max X up to, we're going to look up to the top 50 genes, looking again up to 25. So there is the unadjusted analysis. Again, this is with the very imbalanced design. And if I do the RUVR inverse, it adjusts and looks good. Okay, so again, the main point that I just wanted to point out is that going back to this canonical correlation plot, when you end up with something like this, it can be somewhat hard to interpret. It can mean either that there is confounding between the unwanted factors and the biology that needs to be adjusted for, or it can mean that your negative controls are being somewhat affected by the factor of interest, and it's going to take some thought and some looking around to figure out what it might be. And by looking around, again, looking at like these rank plots and things like that are good. Okay, so I will shut up and get out of the way and let these guys go. I guess I'll take questions too if they're going on.
Okay, so hi everybody, my name is Mari. So now we're going to move to the hands-on tutorial. So we're going to present with Anna, Sebide and Ramyar. We are all from the Walter and Eliza Institute in Melbourne, and we're going to guide you through the tutorial, the hands-on one. So just before, just to make sure everyone has been able to install the packages we will use in this tutorial, and all the material is in the GitHub webpage. So in the first part of this session, Sebide and myself will show you an example of how to use RUV4 for transcriptomic data. Then Anna will show how to apply RUV3. And finally, we have prepared for you small challenges so that you can apply what you have been learning in this session. So I'll start with the first part, how to apply RUV4 for transcriptomic data. So in the GitHub, as it is shown here, if you go to the session 2 and in the folder differential expression with RUV4, and you can open the ARC Markdown, which is called RUV tutorial batch correction RUV4. So I'm going to open the ARC Studio. Can you see well? Yeah? Okay, so in this tutorial, we are going to look at expression data. I don't know, by the way, if is everyone familiar with gene expression data sets? Yeah, so we're going to look at gene expression data that has been combined from, so we put here the reference. It's, we have combined from 10 different microarray studies, and we are looking at samples that are either control or have been TGF-beta treated. So to give you exactly the detail of the study from the reference. Okay, here. So we have here the list of the 10 different studies we have merged in this data set with the different tissue. They have also, they have been performed on different platforms, and you have here all the references for each of those studies. And so here we are interested in this tutorial in doing differential expression. So we want to know which are the genes that are differentially expressed when we apply the treatment with respect to the controls. So to do that, we first need to load the different packages. So you can run with me like across. I'm going to scroll down, but if you want to do it at the same time. So we'll first load two data sets. So in this study, we don't have positive control. So what we have been doing is we have been splitting the data set into two data sets, data set A and data set B. So this is a way to overcome the fact that we don't have positive control. And what we will do is that we will apply the RUV method, and we will compare the results we obtain in each data set, and we would like to see an overlap between the two of them. So we will use that as a trick to see how well we are doing with the normalization method. So if we run this command here, we can see, so we have the two data sets. So I printed here the header of the data set. So each row is a gene, and the columns represent the different samples in the study. So we then load the information for each data set, which is the file info10 data set A and B. And so here we can see that we have the information for all the samples. So each row here is a sample, and you have the corresponding study, whether it's control or TGF-beta treated, the platform that has been used, and also the tissue. All right? So the first thing we want to do here is to assess whether we have unwanted variation in our data. So do you have any suggestion how we could check whether we have unwanted variation in our data set? Any plots that could be useful to see the unwanted variation? Pca, exactly. So we could look at Pca. I'm going to show that in a minute. And then other plot that I also wanted to show, it's called RLE plot. So it's a relative log expression. And I put here the reference of the paper that explains more in detail this plot. But I'm going to explain it here briefly. So basically you can use a command in the RUV package that is called RUV RLE, and you give the gene expression data. So in this case we are looking at sample A, so YA, and we will first run this plot looking at the effect of the study. So we will give him info data set study, and it will generate this kind of plot. So an RLE plot basically is used to see if there is heterogeneity in the different samples. So here we are looking at each box plot is a sample. So we have all the sample in the data set A. And basically in an ideal RLE plot, so just to explain an RLE plot, to compute it, what you do is for all the genes, so for each gene, you will compute the median across all the samples. And then you will remove this median for all the genes in the study, and you will plot the box plot of all the genes in the sample. So basically here, for example, we can see that all the samples from the Deshire study are different from let's say, highest variation with respect to the other study. And ideally, if your data is properly normalized, you would like to have all your samples that are around 0, and the variance should be homogeneous across all the samples. But we can see that there are some heterogeneity in the sample here with respect to the study. Yeah.
So I used the RLE plot in my data set before.
Yeah.
There was a big problem. So sometimes you get the size of the box the same, but
Yeah.
the range quite different.
Yeah.
Sometimes you get the range same, but the box size quite different.
With box size, you mean the quantile?
The middle quantile.
Yeah. Yes.
So which one is important, or what do you expect after normalization or after?
So ideally, you expect that all your sample will be centered in 0,
Yeah.
and the smaller variation possible between the samples.
So how about the size of the box plot?
They should be as smaller as possible.
Smaller.
We will see in the second part of the tutorial some example with applying our UV3 before and after normalization, and you will see how that changes. In this case, because applying RUV4, we don't obtain a normalized data set, so I cannot show you before and after, but we will see an example like that in the second part. Yeah, but ideally you would like them to be as small as possible. So, so here we can look at the effect of the study, but also if we use the platform, so here it's colored by platform, and we also did coloring by tissue in this plot. Okay, so in this case we are interested in the unwanted variation that we want to remove is the study one. So we will focus on that. And our factor of interest in this study is the treatment, whether we are having control samples or TGF-beta treated. So as you were saying, I also provide the code for the sample dataset B. And as you are seeing, another way to look at the unwanted variation is through Pca Plot. So here I made another plot using, again, an RUV function that is called SVD plot that has been presented by Johan before. So here we are looking at the Pca. Each dot here represents a sample, so the shape of the dot, whether it's a circle or the triangle, tells you whether we are looking at control or TGF-beta treated samples. And the color shows a different study. So here ideally we would like that all our samples that have a similar treatment would cluster together. But unfortunately we can see that they are rather clustering by study. So we can really see the unwanted variation in this plot again. Is that clear? So here again we can do the same Pca plot for the data set B, and we observe similar effects. So now let's move on to the part where we apply RUV4. So Johanna explained that the specificity, let's say, about RUV4, that you need to choose how many unwanted dimension you're going to use for your data set. So we will show you now which K to use, which analysis you should use to select the best K. And to do that, we will try with different K values. So to be able to run RUV4, we need to have negative control. So in this study, we are using housekeeping genes. So we will first run load the data coming from the housekeeping gene ID file. And we will define a control, we will define here a control variable that will define our negative control, which is basically a vector with false and true, depending whether it's not or not a negative control for the gene in the study. And then we also need to define our factor of interest. So we are defining it here using the group. So we use as factor the treatment, because our factor of interest here is whether it's control or TGF-beta treated. So once we have defined our negative control and our factor of interest GA and GB, we can then run the command from RUV4. So we also wanted to show you how we are, to be able to see how good we are doing with RUV4, we also perform unadjusted data, which is basically we run RUV4 with a K equal to 0, which is like unadjusted data. And so the RUV4 functions, you need to give the gene expression, YA. You also need to pass your factor of interest that we have just defined, JA, and the negative control, and also the dimension you are using. So in this case, we are first doing the unadjusted case, so K equal to 0. So that will return you a fit for the RUV4, and we are using the function RUV4 summary to access the different statistics from this RUV normalization. And so when we do that, we can, as Johan was presenting previously, we can, if we do a head of the different statistics that come out, we have the p-value and the different test statistics that we obtain for all the genes. So this is for the unadjusted case, and now we will basically define a loop where we will have the k value that we will vary from 1 to 24, and we will run similarly the RUV4 function here, using again the YA, the gene expression data, the factor of interest, the control, and in this case the k value will vary every time in the loop, so that we have a fit for the different value of k. And so now CBD is going to show you how to analyze the results obtained by RUV4.
Thank you, Mari. Here, Mari showed you how we can do differential expression analysis in a data, and also using RUV4 when we adjust the values of k, as you can see here, right? Now I have a question for you. How do we know which value of this k is actually an optimal value? Any idea how we can check for this? Yuan went through that. So we always want to check the canonical correlation plot. So basically there is an RUV can core plot, as Yuan said. We give it the expression matrix YA, for example, and we give it also the treatment group, which is the biological factor of interest, and also we give it the negative control genes. And what it does is that for each value of k, which is here, for each value of k, it actually tells us the S-square of the canonical correlation between the biological factor of interest, which is treatment, and the k first principal component of the housekeeping genes, because now the housekeeping genes are negative control genes. And here we have, for example, in dataset B, we can say that we're pretty safe if we select k until up to 3, because the correlation seems to be small. But as we increase it, it's going to be tricky to select the higher value for k. And this is also similar for dataset A, where we have, for example, k between 1 to 5 roughly seems to be a safer choice for us, while we have a very increased in the correlation value. But to compare how these different values of k can result in differences in the outcome that we get, we try to look at the dataset A and B, which are unadjusted, as well as the dataset A and B adjusted with different values of RUV4, with different values of k using RUV4, and see how the log-fold changes obtained from differential expression analysis change as we change the k value. For example, here we have log-fold change or beta hat in dataset A, and here we have beta hat or log-fold change in dataset B. And we're looking at the unadjusted data. And basically, the higher the correlation is, the better we're doing with the normalization in our differential expression analysis. Here is the unadjusted data, and we can also increase, add k, for example, starting from k1, and increase this k value 2, 3, and increasing that again and again, and we see that the correlation changes. So basically, the log-fold change that we calculate for each of these genes into independent data set change as we change k. So that's why it's really important to select an optimal value for k. But what would happen if we actually go with the k equal to 5, and also for dataset A, and k equal to 3 for dataset B, because according to the canonical correlation plot, we thought that maybe these are a good value for k. And so this is showing you the correlation between dataset A and B, which is pretty much good correlation compared to what I showed you before when we had the same k for the both datasets. Here we have different k for different datasets because it seems to be slightly different when we look at the canonical correlation plot. Another thing that we always need to look at when we do differential expression analysis is the histogram of p-values. What I do here is that I select k for equal to 5 for dataset A, and then k equal to 3 for dataset B, and I look at both unadjusted data, which is k equal to 0, and adjusted data in dataset A and B, and see how the distribution of p-value actually changes. So this is one of the p-value distributions, which doesn't seem to be right, because as Yuan said, it should be uniform for the large values for p-value, and then we need to have a sharp spike for the small p-values. But what we see here, after correction, the p-value the spike that we see here is larger if you compare this with this one, which was unadjusted, and we have a sort of flat distribution for the rest of the p-values, and this is basically consistent if you look at the unadjusted data set B and the RUV4 corrected data set B. Volcano plot also is useful, as showed you before. We again go with those values that we thought were useful for dataset A and B, and again we look at the uncorrected and the corrected to see how they are different. What you see here, we have actually RUV volcano, and we give it the result of the fit that we got. So this is unadjusted, we have log4 change as X, and then we have the p-values for those log4 changes. So in the unadjusted data, if we want to, for example, put our threshold somewhere around here as a log4 change and also somewhere around here, we don't have much or many differential expressed genes in the unadjusted data, and the coloring, I should say, that is related to whether these genes are considered to be negative control genes or not. So if it's true, they are negative control genes, which are the housekeeping genes. But if we go to the corrected version, we see that this significance level here actually increased if you compare with unadjusted. And then we would get more differential expressed genes, which is consistent with what we observed from the distribution of the p-values, right? And this is also consistent when we look at the unadjusted dataset B before and after correction. Any questions so far? So another thing that we can do, because our final goal is to obtain differential expressed genes, is try to define our differential expressed genes in each of these scenarios, and then try to compare those results coming from dataset A and B and see how consistent we are. What's the overlapping number of genes between these two, or whether we're doing a good job in that or not. So I again start with unadjusted data. What I do here is that I define my differential expressed genes as those with the adjusted p-value less than 0.05 and the absolute log4 change greater than 1. I do that for dataset A, which is unadjusted, and also dataset B, unadjusted. And I'll look at the overlapping genes between them using this using this Venn diagram function. So these are the genes that are coming up when I have the unadjusted dataset A, which is 28 genes, and then I have 21 genes in the dataset B, and the overlapping genes is pretty small as well. So this is what we would get if we don't do any correction, we just do a simple differential expression analysis without taking into account that we did have unwanted variation. But then we wanted also to look at different RUV normalization that we have with different values of K. Again, we write for loop here when we give it different values of K, and we calculate, we define differential expressed genes coming for different values of K. We store that here. We do the same for the dataset B. And then here again, I write a for loop when we give it different values of K, and we plot the Venn diagram. And so here are the results. And this is also again showing me something that the correlation plot showed me, the correlation between the log4 changes, because as I change the K value, for example, from 1 to 2 to 3, the number of differential expressed genes that I get is different with different number of overlaps, and so it really matters which value of K we go with. But we can again run this with those value of K that we thought are maybe useful to look at, like K5 for dataset A and K3 for dataset B, and we look at the Venn diagram. And here we have roughly the same number of differential expressed genes, roughly 40-ish, and then the overlapping number is as well like pretty high, like it's 157. It doesn't look bad. Any question? We can also look at each of the data sets separately. We can look at dataset A, because on dataset A we had an unadjusted version and we had an RUV4 adjusted. And we can also look at dataset B separately and then see what would be the overlapping number of differential expressed genes if we do unadjusted or RUV adjusted in one dataset. And so this is an important message coming from the plot that we look at, because this is unadjusted and RUV4 adjusted. You can see that the number of genes that we get as differential expressed is very different. So it means that if we don't correct for unwanted variation, we might end up with a large value or large rate of false negatives, where it tells us that there's only 28 differential expressed genes and we're missing a lot of actually truly differential expressed genes. And we get the similar results if we look at the data set B with unadjusted and adjusted value of the K here. So one thing which is important is that, as Mari said, we didn't have like positive control, for example, to look at something like rank plots. But that's why we split the data into two groups of, say, trying to obtain differential expressed genes in one data set and then compare the result to see how consistent we are. But that would be a great idea always to have some positive controls in advance. So in this case, for example, I want to have some genes that are truly differentially expressed between TGF-beta treated and control, so then I can compare how good I'm doing in the normalizing data and obtaining differential expressed genes. So, but that's one way. If you don't have positive control, maybe you want to do something like a splitting and look at the consistencies between different subsets of your data set. So that's my part for RUV4. If you have any question for this part. Yes?
For the P-value plot,
Mm-hmm.
is that expected to see a spike in the very small P-value and uniform value?
Yeah, that's what's expected.
That P-value here looks like there's almost nothing when it's larger than 0.5.
No, there is. Actually, if I split the y-axis into be very low, you will see the uniformity. It's just like, this is very large, I would say. Yeah, because like, for example, for this one, when we have 5, you will see the other distributions, but I could actually easily cut this, and then we will look at the rest of this, which is uniform. Any other question? Okay, so this part was all when we wanted to obtain differential expressed genes using RUV4. In the next part, Anna is going to tell you about RUV3, and when the purpose of this study is general normalization, when you don't want to do differential expression analysis, but you just want to clean up your data for some unsupervised analysis. Thank you.
Okay, so now, I just want to say thanks to Jan, Sepide and Mari, because they kind of have explained all the hard patterns. Probably for me now, life will be a little bit easier because they've explained all the tools and instruments that we need to go through. So how to check if your data needs to be let me see. If you haven't, because I can't see from here. Oh, give me a minute, because I can't see the is in system preferences. So in the meantime that I'm trying to download the tutorial, if you would like to, so if you haven't opened the R Studio sessions with the RUV3 parts, I suggest if you want to follow it up with me, then if you can do it as well. It should work. Okay, now I'll see this one. Okay, so in this part, as Sepide says, I'm going to show you how we can apply RUV3, which is the methods that help allows you to perform global adjustments. So even if you don't, when you just want to take your data and you want to remove any batch effect that you think my data has in it. So I'm going to start first of all by loading the data into R. So I have this mirror session here if you want to follow the tutorial through GitHub, so you see how everything look like, but maybe I'm just going to make this a tweak again. So I'm going to start by loading the data into R. Maybe make this a little bit bigger. Okay, maybe I'm just going to make it bigger and let's see. Okay, so we start by loading the packages and all the data into R. So here we have, again, we have gene expression data. We have 690 and gene and 950 59 samples, of which I'm only showing you the first 5 rows and columns. And this expression data have been collected through the nanostring technology, which is a technology that you maybe know it. You did yes, so you know it. So it allows you to extract the expression of about 700, 800 genes of interest for you, and yeah, and that's all. Pretty much, it doesn't give you sequence data, but it doesn't even give you intensities for the data that Marie and Sebide were showing you. So it gives you counts. That's why then we need to log to transform this data. So here you see these metrics, and one thing that I also want to mention is that column 1, which is column for sample 1, is a replicate for column 5, which I call sample 1.1. The next step, we load this sample data, which shows you for each sample, which is the sample ID. Sorry, this is called sample IDs, but it should be sample. And it tells you from which batch each sample comes from, and it tells you also which tissue. So tissue is the biology that we would like to see shown in our data, whereas the batch is the different batches with, from which the data have been done. And in the the batches actually refers to different reagents with which the data have been done, and ideally you shouldn't see differences in the expression of data that have been done with different reagents. But of course, since that have been done in different times, and these reagents have been maybe collected at different stages, then of course you might expect to see some differences, which is what you want to first check. And then if everything is fine, then probably you think, oh, my data is okay to be is okay, or otherwise you want to correct. And the method that we will use exploit the replicates in our data. So the key component of RUV3 is that it works with replicates data, which means that you have samples that have been run across different batches. And here is, this is called technical replicate location plot, and it shows you where each replicate is and come from. So every dot is one sample, and their replicate pairs or triplets are connected through a line, which means that, for example, this sample up here is the same, so it is the same biological sample, but a different samples, which has been run in batch 2 and then batch 3, and actually twice in batch 3 and then once in batch 4. So as you can see from here, we have samples that have been run multiple times within the same batch, but also we have samples that have been run across batches. And this is really important because this allows you to capture both the within batch, within batch unwanted variation, but also the between batches one. And yep. This plot actually comes from a more complicated function that Ramyar or Johan created. So I took these pictures from the paper. So Ramyar is the one who worked with this data, and I think this plot was published in the paper that was shown in the paper. Yeah. So we were actually thinking, since it is a little bit complex, so I didn't put it here because it would have taken a lot of lines, but we are really happy to maybe share it later or put the R code in the GitHub folder and share it with you. And okay, so the first thing that we will do is to try to see if there is batch effect in our data. And as Marie and Sepide showed to us, so we can first start by using the Pca plot. And so if I first look at this plot, I say, well, I don't actually see any split in biology, but I don't actually see also split by batch. So you might think that there is no biology, or you might think that there is no batch effect, but probably it is worth checking to further Pca as well. So it is probably likely that this Pca plot comes from maybe some outliers that have been that were there, and they caused this big spread on the first PC. So here is the same plot, but instead of coloring by batch, I'm coloring it by tissue. And again, I do not see any cluster due to the tissue, but maybe, maybe the first component splits a little bit, but it's not really that clear. If then instead we look and look at the, so here instead I'm plotting on the x-axis we have PC1, and on the y-axis we have PC3, and as you can see, PC3 splits our sample by our samples by tissues. Indeed, we have that the blue is the terminal ileum tissue, whereas the purple is the colorectal tissue. We see that they are split by tissue, but also within every tissue there is a split by batch, which means that there is still batch effect that we need to correct for. And it might not be that striking from the first PC, but you need to take that into account, because this will create confounding later if you try to do any other analysis or plots that you might need. So the next thing that also everyone before also showed as well, so it's to try to detect if we have batch effect in our data by looking at the RLE plot. And I'm going to make this bigger. So this is exactly the same plot that Marie and Seppi they were showing you earlier. It's just that since we have a lot of data, we had to squeeze every box plot into a line. So instead of having the whole box, we have a line which shows you the interquartile range, I think, the black line, and every dot is instead a median. And every dot is colored by batch. And as you can see, you notice big fluctuation around 0. And you might think, well, maybe this is actually due by tissue. Maybe all these samples up here are all from one tissue, whereas the other one are not. But instead, if I color it by tissue, I clearly see that even if the samples are from the same tissue, they are very, very, so the box plot of these samples are very different. And if you see something like this, actually, you might see that all these samples up here, I'm pointing at this blue here and the blue here, are actually from the same tissue, but this almost shows that all the genes are very, very different between the two tissues, which is something that you might not think is actually due, it is actually real. And one thing that I also want to mention is that you might see this fluctuation because with the nanostring, so these samples are ordered by batch, but by time. So it might happen that when you process your data with this technology, you also see a time effect that you also want to correct for. Okay, so is there any question until now, or this is all something that we've seen before? So let's now build the matrix of replicates, and as Johan showed before in his talk, we can use the replicate matrix function from the RUV package, and the only information that you need to provide to this function is the vector that indicates the replicate structure of your data. So here, first of all, I created a table from the replicate, and I'm only showing you the samples that have more than one row in it, which means that, for example, sample 1, this comes from the sample information data. Sample 1 has 3 replicates, sample 100 has 2, so we have samples that have 2, 3, or 4 replicates. And the head of the replicate matrix, as Johan was showing before, will show you that this matrix is made by 1 and zeros. And I also plotted this, I plotted here just the first 8 rows, maybe 10 rows and 10 columns. And here you can see that, for example, sample 1, so in columns you have the number of unique biological samples, whereas in rows you have all the samples. And it is really important that you always check that the rows of the replicate matrix that you create are in the same order and exactly the same as the information matrix that you use, as well as the column, as the rows of the expression matrix that you will use in RUV3. And I also want to remind you that this one, I think it was the dimension of this matrix. So here we have that this matrix at 959 rows, which is exactly the same as our number of samples, and 913 columns, which is the number of unique biological samples. And the difference between the rows and the columns is the number of replicates that you have, which is actually the number of samples that RUV3 will use when it does the global adjustment. And so the only thing that you need to remember is that, of course, every row of this matrix will have at least one entry that is equal to 1, whereas every column can have at least 1, but of course more than 1, depending on how many replicates this sample has. Okay, so let's try now to run RUV3 and see what happens. Maybe I didn't run. This ran fine. Oh, maybe I didn't load at the beginning the expression data. And sample information. Okay. So here I'm using as again why I had to transpose the data with the expression values, because you want to have the samples are the rows and the genes are the columns. The matrix of replicates is the one that I created before, and here I'm using, I'm giving as negative control all the genes, so I'm giving an index from 1 to the number of row of our data, and then I'm using the maximum number of k. As we were talking before, there is not one exact way in which you choose k or the number of negative control that you want to use. Here we use this one because actually Ramyar has done a lot of work on this data, and he found that this one was actually the best one. Normally you would like to try iteratively to check, you try 1K in a set of genes, and then you see if the plots look good, and then you check other things, you check for positive control genes, and you see if they look good, and then you try to change it and see if something changes or if it's better. So it's a pretty long, it can take up to a few months, as Ramyar did. Okay, let's see now how they look like. So if I now plot the first two components, actually, I see that there is still a split, no way. Yeah, this is the wrong one, sorry. I need to rerun it again. So if I now plot the PCA1 and PCA2, I can see two clusters, and I do not see a clustering by batch anymore, but I see two blobs. And as you might imagine, these two blobs are actually the tissue of interest, which are now here. So you don't see this difference right in the first PC. There might be still something else, I don't know. But so before we had the batch effect in the first, sorry, we didn't have anything, but we knew that there was still batch effect, whereas now we have removed that batch effect. And if we also plot the RLE plot, we see that it looks as it should look like. So we have all the median centered on 0, and we have the interquartile range, which has more equal. And I guess that's it for me. I don't know what's the time. So is there any question or anything that we haven't explained before? Okay, so we have in plan some challenges. So here one small exercise was to try to run to try to run with this data using different Ks, just to give you an idea of how it looks like. I might just try to do it quickly from here, just to give you an idea of how it looks like. And for the last half an hour, then Ramyar will explain, will introduce the challenges that we prepare for you. And we will give you maybe 15 minutes for you to try to go through them. And then we will try to have a brief discussion about them, about the results later. So I might just show you one, for example. So here, for example, if you just change, and I try to put k equal 1, because sometimes you might want to do that, and then you try to visualize again how your PCA look like. You can see them now instead. You still see the batches in the second component. You see a split, which probably could be tissue. Exactly, but you still see a batch effect. And for example, if we go to 10, so it's sort of like you should try probably also with different set of negative control genes and see how it looks like. So if I go to 10, so you see how it is also pretty easy. Probably from 10, you already see that there is not much, that you kind of did a good job already. And this also comes back to what Joanna was saying before, that probably after a while, you know, it doesn't matter, so it doesn't matter how many Ks you use, probably you will get a very similar results. And yep, so that's it for me.
You can try it, while I'm sitting on the challenge block.
Sorry, what did you say? How?
K equals 46. We try from 1 to 50. You see, you check every.
Are you asking or asking?
Well, I think
Okay,
we
okay.
did the discussion. Yeah, but you did it, so you reply.
Yeah, as Johan mentioned, positive control is a key component for all the studies, not only for reducing tree. Without having positive control, you can't claim that your data is normalized. We have plenty of positive controls here. We have the Pca, the Untitled Plot, and some genes that we know biology, and we use a different case to get that positive controls right. And we are hoping that the rest of the genes is right. That's how we get with different cases. Usually, in output, because I designed this platform, I normalize 8,000 samples from different studies. Usually using RBT, using all genes, and K-maxing works, but not all. It's not the case for all. You need to define the control gene and K, and to get your positive control right, and you should say that you are pretty sure about the rest of the genes that are correct.
You mean there's no like quantifiable way to define K? So let's say by visualizing the RNA plot and Pca plot, and you define this, or there is kind of shape or pattern, then you see if this K works. So is there a way to quantify that?
Directly. Without
Give you some number and you can compare with each case.
I should say no. You should try different cases. As I said, without because I working for this area for 3 years. Without positive control, it is impossible to say that you get your data well normalized. Because there's plenty of papers. They say, okay, we got the data normalized, but they don't show any hint that how the normalization works. It's so important. At least you should have some positive controls. You can be genes and can be statistical plots, out of the Pca and some genes that we call it now in biology or positive control. Okay.
So they are here.
Is a challenge part. You've got 30 minutes. I love challenge. It's your turn. You should tell us what is going on here. I'm gonna take only 2 minutes to explain what kind of data set you have here. And you're gonna split you guys into 2 groups. These guys is one group, and these guys is another group. We've got 2 different data sets. We call it data set 1. Okay. Challenge 1 data. One data set is over-adjusted. We do it on purpose. We over-adjust the data set. One group use data 1 and one group use data 2. A group that received, you don't know which one is over-adjusted. Another one is raw count. A group that received over-adjusted, you should tell us why it's over-adjusted. And another raw data, you should tell us why it's raw. And you need to get it normalized. For this challenge, because it's a real example, this data set comes from a paper published in Science. It's very, very complicated. It's very challenging. And that's why it's selected for this tutorial. We have got 100 genes. We call it control genes. As can you see here? If a group receives unnormalized data set, we should use these 100 control genes. We try different control genes. We select this one works quite well for this data set. We have got the sample information. I'm going to give you little bit hints. In this data set, you have got 5 biological conditions. Is a T cell treated with different treatments. We have got 2 conditions for 48 hours treatments. We have got 3 conditions for 4 hours treatments. The 4-hour treatments run together, we call it round 1. 48-hour treatments run together, we call it round 2. It's kind of complete compound effects. And we have got, in the sample annotation, we have got gender, female and male. And in the gene set, we have got 2 genes, which is on Y chromosome. As Johan mentioned, these genes should be expressed in male and shouldn't be expressed in female. That's a hint to ask this challenge. We give you 10 minutes to 50 minutes. This group use data set 1. This group here use data set 2. A group receive over-adjusted, tell us why it's over-adjusted. A group receive raw count. They should use these 100 genes to get a normalized. And tell us how normalization works. Time, start. This one data set 1, and this group data set 2.
Did you mention the gender genes?
Yeah, you've got 2 genes in the gene list. It's a gender gene. Is our positive control.
Yeah, so if you go into the challenges part here, actually all the hints are here, and we also say, so if you want to consider to look at the expression of the gene on the Y chromosome, ZFY and EF1, in order to inform your decision, because as it was saying, it's a pretty challenging and tricky part.
Over-adjust, I mean over-normalized. It's not a well-normalized data set. You should tell us why it's not a well-normalized data set. You can use Pca, RLA, gender genes to tell us why it's not a well-normalized data set. SAP Anna Mari are around. If you need a little bit cheating, if I ask them. can get help from your group, remember? You can talk together. In each row, you can have one in a group. Which group received the forward adjusted? We don't know yet. We extended the deadline. A 4:45 is a half deadline. Have you got a key? No, we don't have a key.
Don't be shy to ask the question.
Just to mention again, the aim is to get the data globally adjusted. It's not in IO3 example. We don't want to do a differential expression analysis. You've got 5 minutes to go. It's a real example. It's published in Science. It's a very complicated system. But you should tell us that why is over normalized or too normalized. Minutes. Discussion over, which is only 60 seconds. Okay, time's over. I call you right group. You received the Yeah, reciprocal or normalized. Row, 1, 2, 3, yeah. This guy says you have row. Okay, let's say row. For data, and you should get the normalized, isn't it? Can you tell us why this is over-adjusted? What did you find that the data?
Not quite sure now, but I think it looks too nice. I can tell from the report that this data must be original line, but I'm not quite sure how you say that it's over-adjusted.
You actually got the results. So if you
Yeah,
got gender genes,
I'm still following that. I haven't finished that.
gender plots like that's great.
Yeah, I haven't finished that, so.
Okay, great. You receive a raw data set, and this group receive or chosen over-adjusted data set. I'm going to show you the solution. We're going to put on the solution on our GitHub page later on after the workshop finishes. I'm going to show you some key points. We read information, data 1, data 2. If you just study with already plot, we have close to 2,000 samples, and the already plot, as Anna mentioned. Each point is a median of the box plot and the interquartile. Like you can see this is unnormalized data set because already is very noisy. It's not centered around 0. This data set is unnormalized. Okay? And I'm going to come back to this data to get it normalized using that 100 genes. But if I go to, okay, this is a data set that this group found is over-adjusted. If you look at our plot, it looks like perfect. The key point about our plot is a bad our plot shows there's something wrong with your data set. But a good our plot is not sufficient to tell. It's a good sign, but you need to get more positive. It's very important. R is not enough to show that your data is very normalized. You look at the medians all centered around 0. If you look at the PC as well, it looks good because we get the all clusters separated by biology, and PC is good as well. You've got a good ROE with PCA. But there are enough to tell people, to convince people that we get your data normalized. We need some positive genes, positive control. In this case, we have got a Y chromosome gene, or we call it gender genes. They should be expressed in male, and they shouldn't be expressed in female. We don't know whether express one in male, whether are affected by this tip or not. But we know that they shouldn't be expressed. They shouldn't be expressed in female. We should get that flat or without any counts or very noisy or any fluctuation for that. If you look at these two genes, you can see this ZF1, EF1, AY. Look at these triangles are male. They have expression. We don't know if this pattern is correct or not because maybe the gender genes are affected by biology. But look at the female, all should be stable because they are not expressed. You can see this pattern is big. It's like a 2 or 3 for chain differences between condition in a not expressed genes. It shows that your data is over-adjusted. Even PCA is good because we have got a confounding effect here. PCA and ROA, in this case, cannot tell the data is normal. If you look at these two positive genes, which is quite easy to do, the gender genes, we know that they should be stable. They shouldn't be expressed. This pattern should be stable. At least you can see, okay, this data is normalized. If you go to the raw data set, is a question here?
So can you always use those gender genes to see if your data is properly adjusted?
Depends on if you have your, because it's a targeted panel, it's not a genome-wide. In fact, you've got only 250 genes for this set. Because they were quite smart, these people, they add these gender genes for controlling some part of the experiment. It's very, very well known, very good positive. But in the treatment, you always have gender. It's one of the good control, positive control, if you have female and male.
So you can always use
Let's say if you look at the breast cancer data set or our female, using gender pointers. But in this case, yes. Let's go to this. Because as I said, these 248 hours run in this biology and they all run in round 2. And all these 3 guys run in another batch. We have got a confounding. It is a 100% confounding. This Pca cannot tell us how much this separation is because of biology or because of fracture. And as I said, RLA, a good RLA plot, a bad RLA plot shows there's something wrong. A good RLA plot is not enough. We need more evidence for it. Let's go to raw data set. The RLA data set, you can see that these 48 hours show quite the same patterns because they are together. These 4 hours conditions, they show quite the same pattern because they are run together. This RLA shows your data needs to be normalized. Okay? If you look at the Pca, you see you can get that this is a very spread Pca because it's quite noisy, it's a raw count. And if you look at the raw count without any normalization, you can see that the gender genes in female are pretty safe. They are pretty close to the background noise. You've got 2 counts in low, close to the background noise because you usually see some background counts on this plot. But in a female, you've got expression, and the separation is important because you can get that separation between these 2. You can see between this group and this group, you can see male are separated from female. I forgot to say in a over-adjusted data set, which is here, except from this pattern, and you can see that the genders are mixed up for this condition. You can't see the separation anymore for this treatment. You can see that all 3 angles are mixed up with solid points. Even for this condition and for this condition. You get the gender separated for these 2 conditions, but for these 3 conditions, we get this gender because it's over-adjusted. Okay. Is a raw count. We try different because it is very, very specific panel of genes. They are supposed to be differential expression between these conditions. We can't use all genes because, as I said, they are not. We have got confounding effects. They are very, very specific type of genes. In this case, we tried different number of K and different number of control genes. We ended up with 100 genes. Be very useful for this data set. If we run REV3 using our technical replicates, 100 genes as a negative control, and we can get a good RE plot. Quite the same Pca in the over-adjusted. When you have the confounding effects, this Pca cannot help you because you have a confounding effect. This is the same Pca that we get for over-adjusted. But if you look at the gender genes, we see a little bit fluctuation still, but pretty stable. It's not that that we saw in over-adjusted, and we can get that separation for these 3 conditions that we couldn't see in over-adjusted. It tells us, okay, your normalization helps in these conditions. You've got 5 minutes to ask your questions about this challenge. Key points: RLA, a good RLA is not enough. When you have a confounding effects, Pca is not enough. You need to have some positive control. Positive control, this idea from Johan is great. You have to have it for all the studies. Without positive controls, nobody can claim data is normalized.
If I design a study, and this patient study or a human study, then it would be advisable always to have female and male basically samples in that study to have potentially the possibility.
We use gender genes as a kind of positive control, but you don't have to do it all the time. Let's say you are interested in breast cancer. Well, you should do a colorectal cancer with the breast. In the breast cancer, you've got plenty of known biology. For example, different subtypes. We know that is a very known biology. For breast cancer, a first Pca should separate ER positive from ER negative. This ER in a breast cancer in a female is a very well-known positive for us. And Sepida used this kind of positive control, and she tackled one of the data set with batch effect. ER should be separated. The more known values you have, you're more confident about your results. But you don't have to add, if you are not interested in a female or male together, you don't have to add it just because of having positive control. For all the different studies we have, I'm sure you have some known biology that we need to check it after your normalization. Any more questions about the challenge? It was hard, I know, because you don't want to use a very simple challenge when you deal with a real data set. Oh, it's really, really complicated. But it's really one of the complicated data sets that we were dealing with it. And because in a real example for this data set, they sent us their RLE plot. They said, okay, data is zero normal. You don't have any problem. But RLE in this case, good RLE is not enough, Pca is not enough. And especially for panel of genes, because they are selected on purpose. That's really difficult. They have confounding effects. You should have positive control. I'm going to repeat it again. Positive control is so important. Plus replicates, plus negative controls. And positive is so important. I should leave it to you to close the... Thank you very much for listening.
Thanks all of you for coming. I'm really glad to see everybody here. I wanted to say, well, other than thanks, please feel free to contact me or any of us if you have any additional questions, either in the near future or in the long-term future. So there's plenty of very complicated data sets out there. If you ever run into one and would like to ask for any assistance, please feel free. All right, so thanks again. I'm glad you're all here.